In this video, you will learn some basic facts about soils as a construction material. You might be saying to yourself, well, why is the topic of soils important to me? And the answer to that question is that regardless of the types of structures you may build in your career, they will all be supported by soils. Let's begin with a little background on soils. For example, where did they come from? Well, in terms of geologic time, all soils originated as rock. A good way to visualize soil grains is that they are simply baby boulders, created from larger rocks through a process called weathering. Okay, so soil grains at some point came from rock, but just what is soil? The answer is that soil is actually a matrix made up of several components. Starting in the upper right, we said that soil is a matrix. Understand that most types of soil have grains that are generally spherical in shape. We would call it a matrix since it has two components, the solid spheres, and the space between the spheres, which is called the void or pore space. Let's focus next on the larger image of the matrix below, and specifically on the void space between the grains. Soils will have some combination of both water and air filling that void space as shown. The amount of water in a soil is called the soil's moisture content and can be determined with a simple test. Another way to visualize soils is with the use of a phase model like we see to the left. Keep in mind that the void space and the amount of water in a soil is highly variable. Next question. How can a contractor learn about the soils on his project site? And the answer is by reading the geotechnical report. In making this important report, a geotechnical engineer examines the site and performs standardized tests on its soils. From this, he will make specific recommendations to both the structural and civil engineers relative to the earthwork, foundation design, and also any anticipated structural settlement. If you think about soils, they are unique in a number of ways. One example is that they were always present on the site. Now this might sound a little silly, but if you consider all other construction materials are specified, ordered, and delivered to meet project requirements. But the soil comes with a job, for better or for worse. Additionally, soils can be highly variable in their composition and suitability for construction use. Not all soils are capable of supporting the structures we need to build on them. Also understand that most sites will have different layers of different soil types, and that soils will also vary horizontally across the project site. There are a number of ways in which soil is classified or otherwise described. Let's take a look at a few of these. Soil horizons is a common way to describe the vertical layers of soil on any site. The horizon description does not classify soil as to type, but simply establishes a common terminology to describe soil layers. The first horizon which may be present is the O or organic layer of root mat or accumulated plant material, like you might find walking in the woods. Topsoil is the A horizon that is under the organic layer, or in the absence of a O horizon, it may be the top layer present. Topsoil, as we know, is rich in decomposed organic matter which supports plant growth. The subsoil or B horizon will contain roots, insects, and the vertical movement of rainwater from the A and O horizons. Over geologic time, the B layer becomes enriched with organic matter and slowly turns into topsoil. The C horizon is the parent source for the B layer, which in turn parents the A or topsoil horizon. The C layer may contain large rock fragments as well as soil without any organic content. The final horizon, though not illustrated, is the R or solid bedrock layer. So there we have a horizon description of soils. A second way that is used to describe or classify soil is whether the soil is plastic, that is, can be shaped like a child's modeling clay, or non-plastic, like a handful of sand. Our third classification method is according to the grain size of the individual soil particle. This is significant since there is a wide range of particle sizes, and it's also a useful way to predict a soil's behavior. Let's take a closer look at this. Before we go any further, let's identify the basic types of soils. Here we have the basic types in descending order of grain size. One additional soil type, peat muck, is essentially pure organic materials matted together like you might find in a swamp or a bog, and they are not differentiated by their grain size. Realize that sometimes these basic soil types will occur in their pure state, but more often than not they will be found in some combination. The soil we call loam, for example, which is great for farming or gardening, is really about 40% each of sand and silt plus another 20% of clay particles. Let's learn how geotechnical engineers identify these different types of soil. With the exception of organic types, here's one standard for classifying soil according to grain size. If you look, we can see at the top cobbles, and a cobble is defined as being 3 inches or larger in size, so it's a piece of rock. The gravel and sand categories, as we see here, are further broken down between coarse and fine according to their size ranges. And lastly, we see that both clay and silt are categorized as fines, and these are not capable of being distinguished by a sieve analysis. In making a sieve analysis, the sieves are stacked from largest size to smallest with a pan at the bottom. After shaking, the soil particles retained on each sieve are weighed and the results tabulated and graphed. These results are known as the gradation of that particular soil. The sieve analysis method is important because in addition to classifying soils, it is also used to specify aggregates, that is crushed stone products, used in many aspects of construction, such as concrete and asphalt mixes, mortar, road base, drainage layers, etc. Let's take a second to look at this specification by gradation aspect. Here is an example from the Alabama Department of Transportation specification book. Down the left side of the chart, we see the different ASTM standard aggregate number types. And across the top, we can see the various sieve sizes. So for example, if the specification calls for a number 7 aggregate to be used in a concrete mix, we can see that it will have rock particle sizes mainly in the 3/4 inch down to the number 8 size. So we have just learned a little bit about classification and specification by grain size. Let's just take this one step farther. By using gradation and a plasticity test, all soils can be fully classified with specific names or numbers under 2 industry-wide systems. The American Association of State Highway and Transportation Officials, or AASHTO for short, has a very detailed system focused on roadways and pavements. The ASTM, or Unified System, while less exacting, is more generally used for building sites. Just 2 more unique soil attributes to wrap this up. A really unusual feature of soil is that its volume will expand and contract, or shrink and swell as it's called, with any change in the solid to void ratio we just talked about. This shrink and swell of the soil can have very significant cost implications to a contractor and will be the topic of another video. And in order to use soils as a construction material, they normally require compaction or other types of modification. This too will be the topic of another video.